So what is the motivation behind this project? So we already have lots of ways of 3D imaging live tissue and living organisms, but the idea is to study the optical and mechanical properties of this complex biological media, and also to combine two advanced techniques, so fluorescence microscopy and Brillouin microscopy, as well as trying to do something interdisciplinary, because my PhD project is a collaboration with Restor as well as ONERA, which is the Aerospace Lab France. So to give you a context about what our team does at Restor, we work on mammalian adult tissues. So mouse tissue mainly, so tissue repair, to understand how tissue repairs happen in mammalian adults. So we take the subingual adipose tissue. Once it's removed, it's treated with naloxone. And with this treatment, we try to understand if there is a scarring or a regeneration. And it is seen that when this tissue is treated with naloxone, there is a regenerative pattern, but when it's not treated, there is scarring. And we also have a team working on a mathematical model which allows us to understand that the regeneration and scarring also depends on the micromechanics of this ECM. So to give you an idea of, so this is the adipose tissue, and this is the adipose tissue treated with PBS and some staining done on it. And in the next slide, I'm going to show you. Okay. So when the tissue is treated with just PBS and when the tissue is treated with naloxone, you can see the difference in scarring and the difference with regeneration. Now, how is this project going to help the the information that we have using fluorescence microscopy? Here comes in Brillouin Light Scattering. So Brillouin Light Scattering it's not a new concept, but Brillouin microscopy is quite new. So Brillouin Light Scattering is an inelastic form of light scattering where interactions happen between photons and phonons. So this inelastic light scattering is dependent on temperature and also density. And this lifetime of a phonon is inversely proportional to the line width that you see here. Just to give you an idea of the difference between elastic scattered light and inelastic scattered light. So elastically scattered light can be Rayleigh or Me. And if I have to compare it, elastically scattered light would be the Eiffel Tower, and inelastically scattered light, that is Brillouin scattered light, would be an ant. So if I have to try and get the information from any tissue for Brillouin scattering, I need something known as a spectrometer, and I will be explaining that later. Also, just to give you an idea, this Brillouin frequency shift that you see here and here, this is what is going to give me the longitudinal modulus of the cell, and in turn going to give me the mechanical properties. So this is taken from an already published paper. Here I have the idea of how my shift in turn gives me the viscoelasticity. So regions which have a lesser Brillouin shift have low viscoelasticity, and regions which have high viscoelasticity have high Brillouin shift. What is the biological context behind this entire project? So we already know that Brillouin shift, I have a difference in Brillouin shift with the stiffness, but I also have a difference in Brillouin shift with temperature. So it's really important that when we do the entire imaging, or when I do the entire testing, the ambient temperature should remain the same. Okay. Now, coming to my project, to give you an introduction, I'm already using the setup that I'm using. It's similar to two setups that have already been developed by Zhetao Zhang in the US and by Carlo in AMBL Heidelberg. So this system uses a single illumination objective and two detection objectives placed back to back, as you see here. But the system I'm building has one illumination arm, so we use a single laser, but the same thing is used for fluorescence as well as Brillouin. because the idea is when I have the fluorescence map, I also have my Brillouin scattering so that I can compare between these two. So I'm building the setup from ground zero. So I'm building it from the beginning. We started with just an empty laser bench and something which is super important in my project, the VIPA. It looks like a piece of glass, but I will explain how it's really important. And we already have a laser bench with the cobalt laser of 532 nanometers. So the VIPA, or the virtually image phased array. Thanks to RTM-FM, we have this VIPA, and it's a glass echelon. So it's a piece of glass, but it has different reflectivities on either side. So the material is fused silica, and just a small thing to remember, the input window is just 3 millimeters. So my signal needs to go through this 3 millimeter input window. Why did we choose a VIPA over other spectrometers like the Fabry-Perot? The Fabry-Perot has moving parts, but the VIPA is a single glass echelon which does not have any moving parts. So in theory, it should be easier to use than the Fabry-Perot. But the challenges come where I have to place my VIPA at a 1 degree angle to actually have the incident beam hit the reflective surface, which is 95% reflective, and cause multiple reflections inside the glass echelon, and finally have virtual images behind. So the resolving power is good enough because the reflectivity of the back surface and the front surface has been decided, and we don't have to change the distance between these two glass plates. And you have a sufficiently large angular dispersion so that it separates the Brillouin-Stokes and anti-Stokes from the Rayleigh peak. And it's, as I said, it's an improved version of the Fabry-Perot echelon. So how am I going to use the VIPA to actually get the Brillouin spectrum? Okay. So when my incident beam goes through the VIPA, it has multiple reflections. I have my virtual images, and I use a lens to finally image it on the camera. And in the camera, if I use two VIPAs, as seen in this figure, I would be getting points. So in this, I have the Rayleigh scattering, the Brillouin anti-Stokes, and the Brillouin-Stokes. But if I use a singular VIPA, actually I'm going to see lines. So I'm going to see one line in the middle of of Rayleigh scattering, and on either side of Brillouin-Stokes and Brillouin anti-Stokes. So aligning the VIPA. When we first started, the alignment of the VIPA was done with just a cylindrical lens, the VIPA, and a spherical lens with a camera to make sure that my VIPA is aligned and to actually learn how to align it. And it was quite hard because usually the alignment done at Montpellier when they started out. So we had a lot of help from Montpellier. When they started off, it took them, I would say, 6 months to a year to actually learn how to align the VIPA. But because we had help, I think it took us 3 to 4 months. And when the VIPA is orthogonally aligned to the cylindrical lens, I see just a point. But with the change of an angle of 1 degree, I actually see this, and we call it a Christmas tree because it looks like that. These are my virtual images, and the lowest band has the highest intensity, and I have a decreasing intensity as I go upwards. So these are actually different orders. And what I need for Brillouin, when I actually image a sample, I would need at least 3 orders. This is the optical diagram of my system. As I said, we have just one illumination. So the illumination path goes to the sample. And then I have 2 detection objectives. So this is another modality which we have for forward, backward also. And then I use a beam splitter for SPIM detection. And all of this is for my Brillouin detection. So I have a couple of lenses, then my VIPA, and I use cylindrical lenses because we're trying to follow the same path that Zhitao Zhang followed. And then I have the Q-CMOS camera. So why the Q-CMOS camera? Oh, sorry, and I forgot this. So there's something called a galvo mirror that we use here. And the novelty in my project comes from the fact that it's a digitally line scan Brillouin microscope. There already exist line scan microscopes, but nothing which is digitally line scan. And this digital line scanning comes from the galvo mirror, also the QCMOS camera. And I can tell you how. So the galvo mirror is essentially two mirrors placed at 45 degrees, but these are connected to a board and also a LabVIEW program. So this allows me to scan in two directions by changing the amplitude as well as the frequency. So I can essentially scan my sample. So when I use the galvo mirror, and I also have a flip lens, so at the same position, I can change between a spherical lens and a cylindrical lens of the same focal length. So when I use a spherical lens, I see a line of light, and this is my illumination path. So my laser, I have my spherical lenses, I have my galvo mirror, then again a combination of spherical lenses. And this S4 is actually what changes to spherical and cylindrical. And this is when I use my galvo mirror to scan, to give you an idea. So the scanning frequency here is 100, and I've left the scanning amplitude as 1. And I can change the scanning amplitude to 1 to 10. At the same time, when I change the S4 to a cylindrical lens, in this orientation that you see here, I would get the entire plane illuminated. But just to have an idea, I've placed the cylindrical lens at 90 degrees, so 90 degrees from this orientation to see how it looks like. So it would give the cylindrical lens in this orientation gives me a sheet of light rather than a line of light. And further, if I use my galvo mirror, it would increase my field of view. So how is the digital line scanning going to happen? If I'm able to conjugate my frequency of the galvo mirror as well as the frequency of my camera, that's going to give me a rolling shutter option. So the So the QCMOS camera has the option of a rolling shutter. So the rolling shutter is something you can control the frequency of your shutter. So when I illuminate my sample with a scanning of my galvo mirror, I can do the same with the rolling shutter and therefore have digital line scanning. So if you look at the system here, this is where my illumination path is, and I have my galvo mirror. And I also have my physiological chamber, which with stages I can move. And behind this black surface here is the Quest camera. So the Quest camera has a very large field of view and the effective area. So with this, we've done some calculation to find out the lateral resolution that we have right now is 1.3 micrometer. We did start off with a detection objective of 10 placed back to back, but with further research, we've found that it's better to use a 20 and a 5. So sadly, we still don't have a Brillouin spectrum because it's quite difficult to actually even image a Brillouin spectrum without a suppressor for the Rayleigh peak. So in this case, we should be using an iodine cell or a notch filter, and we still have to implement that into the system. But right now, we know that our VIPA is well aligned because you can see the virtual images after the VIPA. And we also know that the galvo mirror scanning works well. And since the rolling shutter function is available on the QCMOS, we are expecting that when we conjugate, we do have a digital line scanning, but we are still in the process of capturing some Brillouin signals. So, as I said, we need to find a suppression for the Rayleigh peak, but also because, like I said, the difference between the Rayleigh and the Brillouin peak is so large that instead of using a beam split of 50-50, where 50 goes for my fluorescence imaging and 50 goes for my Brillouin imaging, we're planning to use something like 80-20 or even 90-10, so that all of the power of the laser and all of the information goes to the Brillouin and much lesser to the fluorescence side. And we're also trying to use another Brillouin system, obviously not a digital line scanning system because only we have that, but another system to try and image the adipose tissue so we know how it behaves. Thank you very much. And also thanks to the entire team at Got It. Oh, cool.